Hello and welcome to Diplomatic Derivatives, a platform where we tackle different concepts of pure mathematics. We have started with the group theory, and in today's video we're going to discuss the different types of groups, including the torsion-free, mixed, semigroup, monoid, and the abelian group. We have slightly touched the topic of monoid, but here we're going to go into detail and understand what these different types of group means. So let's continue. This topic is the torsion-free group. But before understanding what a torsion-free group is, we will just revise in a very slight manner. A group, we know that a group needs to follow 4 group axioms: closure, associativity, identity, and inverse. Now, make sure you give emphasis on the part of inverse because that's what's going to be important throughout the lecture. Now, the second thing that we already did is the order of an element. So a raised to n is equal to e. This means that for any element, we will perform the operation of the group on a single element a number of times until and unless we reach the identity element. So let's suppose if the operation on the group is addition. So we have to take an element a, and you keep on adding a plus a plus a plus a, is which will eventually give us e. So that is the number of times the operation is performed on a to get the identity element is the order of that element. Okay. Now the new concept here is finite order. If an element has finite order, it means that after applying the operation a certain number of times, you return to e. So there is a certain number of time for which the operation has to be performed on an element. So let's suppose if we take a plus a plus a is equal to e, so you did the operation 3 times, right? Therefore the order of a will be 3. Okay, so that's a finite order. Now, what is an infinite order? And if an element has infinite order, it means you can keep applying the operation forever and never return to e. So that means that you keep on doing the operation and you are never reaching e. Okay, therefore the order is infinite. All right. Now, in this concept of a finite order and infinite order, we have the concept of a torsion-free group. A torsion-free group is one where every non-identity element has infinite order. Therefore, it means that when we keep on doing the operation and we never reach e. Okay, so you will never cycle back to the identity element. All right, therefore each element has an infinite order. Okay, that group is known as a torsion-free group. Apart from the identity, the rest of the elements, okay, also known as aperiodic group. Okay, this is also another name of a torsion-free group. We take an example. Consider the group of integers under addition, that is z, with operation of plus. Now this is not z plus or z minus, it's a complete integers group. Therefore we have 0, we have all the positive numbers, and we have all the negative numbers extending in infinite directions. Okay, now since the operation is addition, the identity element of this group must be 0, right? Now we take any element. Let's suppose if we take 1, we have to perform the operation and we need to circle back to 0, right? So you take 1 plus 1 plus 1 plus 1 and so on, and you will never be able to reach 0, right? Therefore 1 has an infinite order. And similarly, you perform a similar operation on the rest of the elements and you will realize that there is no element for which you will reach to 0, right? Therefore all the elements in this group are having an infinite order except for the identity. The rest of the elements, because identity itself is, e, right? So apart from identity, nothing circle backs to the identity. Therefore the set is known as, this group is known as a torsion-free group. Now another small concept, just to write in the same slide, we can see that there's a term known as periodic group, all elements having finite order. So this torsion-free is a group which has all elements having infinite order, which is also known as aperiodic, and a periodic group having all elements having finite order. Okay. Mixed group. Now a mixed group is a group that has both elements of finite order and elements of infinite order. So you have both type of elements in this group. All right, now we see an example. Consider the group z into z2. Now z is the group of integers, as we saw earlier in the previous slide, that z is integers group which is torsion free. All right, then this is a combined group. Okay, so z, and then it's combined with another group which is z2, which is a modulo addition, which is a modulo group, right? Z2, that means that there are 2 elements in the group, and those 2 elements will start from 0 because it's z. So 0 and 1 are the 2 elements inside this group, right? Now if let's suppose you take 1, Okay, now what is the order of 1 in this group? How will you check that? It's addition, so you will add. You will add 1 plus 1, which gives you 2, right? And since it gives us 2, 2 will circle back to 0 since it's a modular group. For understanding this concept, you can refer to one of the previous videos where we explained this concept in detail. So in a modular group, what happens that you have a cycle, and it's also known as a cyclic group. And what happens is you take 1 plus 1, which is 2, and since 2 is not part of the group, it will circle back to the first element, and then it will continue to each of the elements. So each element is assigned the next value, right? So 1 plus 1, 2, and 2 circle back to 0. So you get 1 plus 1 is equal to 0, and 0 is the identity element. Therefore, this 1 has the order 2, and this is a finite order. Therefore, so now we have another concept, which is a semigroup, and then we have a monoid. Now these are very simple concepts. A semigroup is simply when a set has an associative binary operation, it's called a semigroup. So when we're trying to prove that some set is a group, we take the 4 group axioms, right? Now the second group axiom is associativity. When we reach the second group axiom and we try to prove that the group is associative, that means that now we have proven that the group is a semigroup. So if the group is associative, it's called a semigroup. Okay, for example, a set of positive integers with addition. Addition is associative, so positive integers under addition form a semigroup. Now after proving that a group is semigroup, we will prove that it has an identity, which is a third group axiom, right? And once we have proven the group has identity, therefore that group will be called a monoid. Okay, so the set of all integers including 0 with addition is one example. Addition is associative, therefore the group is semigroup. The set is semigroup. 0 is the identity element, so the identity element exists, therefore the group under addition forms a monoid. Okay, next we have an important concept which will be used in the future videos as well. It's a very important concept, the abelian group. Now we know that a group already means it is having an associative operation, therefore it's a semigroup, an identity element, so it's a monoid, and also every element has an inverse, so inverse exists. Okay, now if the operation is also commutative, that means that the operation of AB is equal to BA exists in the group. So after proving the 4 axioms, we come to the 5th axiom to prove that A operation B is equal to B operation A. If this is true, that means that the group is commutative, and that commutative group will be known as an abelian group. So we take examples and we explain it in detail. First one, Z, Q, R, C under addition are abelian group, that is integers, rationals, and reals, and complex numbers. Now these 4 groups, we have to prove that under the operation of addition, these are abelian groups. Okay, it means that commutative property is true. So first, in order to prove that it's abelian, we have to prove that these are groups. So how do we prove that? Addition is associated. So take any 2 numbers. Let's suppose you take 2 and 3, right, from integers. 2 plus 3 plus 4, okay, also you take 4. So 2 plus 3 plus 4 is equal to 2 plus 3 plus 4, right? So it's associative, that's true. There is an identity element, yeah, so in integers we have 0, and it's true for the rest of the groups as well, sets as well. So 0 exists. Every element has an inverse, so since the addition operation is addition, and we take an element A, so its inverse has to be minus A, right? And it's true for all the groups, all the sets as well. Now, therefore, now we have proven that these sets are groups. The 5th thing is now going to allow us to prove that they are commutative as well. So A plus B is equal to B plus A. So 2 plus 3, 5, 3 plus 2, 5. So it's true. It's true for the rest of the sets as well. So this group is also commutative. Therefore, these groups are abelian groups under the operation of addition. Okay, so it's simple, but it might get complicated in the other concepts that we're going to do later. For now, this is the basic manner in which how we prove that the sets are groups, and then that those groups are abelian. Another example, this is one of the examples for which we have done a detailed video earlier as well. Positive integers under addition are not a group. So if something is not a group, we don't need to prove if it's abelian or not, because it's simply not a group, so it can't be abelian. Set, we take Z positive, which is the set of positive integers. Operation is addition. For detailed video, you can just check out one of the previous videos with the name of this group itself, where I have explained this in detail why it's not a group. So make sure you check that. Positive integers under n multiplication are again not a group. Also in the same video this is also tackled, so make sure you check why it's not a group. Next is positive rationals, reals, non-zero rationals, reals, complex under multiplication are abelian groups. So now these are the groups we are tackling with: positive rationals, positive reals, and non-zero rationals and non-zero reals. So these are, there is no zero, okay, and complex numbers. Operation is multiplication. Since the operation is multiplication, the identity element is 1. Okay, so we don't need to worry if there is 0 or not, because 0 is the identity element for addition. If there is no 0, it's okay, because the operation we're tackling is multiplication. And under this operation, it is associative. The identity element is 1, which exists. Every non-zero element has an inverse. So for the identity element 1, the inverse has to be 1 by of the element, right? So if it's A, so inverse has to be 1 by A. Multiplication is commutative as well. Therefore, these groups are abelian groups, okay, under multiplication. Next is matrices. So all m by n matrices under addition form an abelian group. So all m by n matrices, and the operation is addition. Now addition, matrix addition is associative. When we studied matrix in 11th and 12th grade, 9th and 10th grade, we already did how matrices work and what is matrix addition, and we did that matrix addition is associative, so try to remember that. Identity element is the 0 matrix. So since it's addition, the identity element is 0, and for matrix addition the identity element will be the 0 matrix, that is all entries are 0. Every matrix has an additive inverse, so the additive inverse for matrices is just negate all the values. So if it's 1 2 3 4, so the additive inverse will be -1 -2 -3 and -4. Also matrix addition is commutative, so it's an abelian group, okay. Then n by n matrices under multiplication are not a group. So it's the same thing as this, but the difference comes here is that matrix multiplication is not commutative. We already also studied that AB is not equal to BA, right? Therefore, matrix multiplication is not commutative. So this matrix under multiplication are not abelian groups, okay. They are not a group, also because 0 matrix has no inverse, so the inverse of 0 matrix does not exist, since 0 is also a part of this, right? In the previous example we saw that for multiplication and the groups were non-zero, right? Therefore 0 was not a part of it, so it's okay, 0 will not have an inverse. So since 0 is not even a part of those groups, we don't need to worry about 0. But here in this matrix, 0 is a part of matrices, right? So 0 has no inverse, therefore you cannot say that inverse exists. Therefore it's not a group itself. So if it's not a group, we need to check if it's abelian or not, okay. Now another concept is finite and infinite group. Very easy concept. A group G is said to be finite if G consists of finite number of elements. That is, there is a limited number of elements inside the group, and it's said to be infinite if it consists of infinite number of elements. So let's suppose Z, a simple integers group, it has 0, all negatives until infinite, all positives till infinite. So it's going till infinite, therefore the number of elements are infinite. It's called an infinite group. But this group over here, G is equal to 1 minus 1 iota minus iota, the order of the group is 4, right? Since the order is 4, it's a finite order, so we call this group as a finite group, okay. So that's a very simple concept there. All right, that's it for this video. I hope the concepts were made clear. The major concepts of types of groups are quite easy, but just abelian group part has to be dealt in detail. And also we'll be tackling this concept in future videos as well, when we'll be talking about the next concept, which is the Cayley's table. So that will come there as well. Make sure you like, share and subscribe the video if you like the content, and if you have any queries, you can ask me in the comment box below. So that's it for today. See you in the next one. Thank you.